Hello, in this video we look at the ratio test for convergence of a series. Now I have three background videos: the limit supremum, limit infimum of a sequence of real numbers, the geometric series, and the comparison test for convergence of a series. We'll use all three of those here. The theorem that we're going to look at in this video is this: let this be a series with non-negative terms, and this for all n, and let R be the limit supremum of this ratio, and let little r be the limit infimum of this ratio. Then the sequence, an, converges if capital R is less than 1 and diverges if little r is greater than 1. Now in BV1 we looked at what the limit infimum and limit in supremum are, and it's basically that as we look at each ratio, so we go down each term and look at this ratio, these are going to bounce around. Some may be big, some small, but if we get one value that tends to repeat infinitely many times, that's what's called an accumulation point. And there may be more than one accumulation points, sometimes called limit points. Then if we take the limit supremum of those accumulation points, that's what R is. And those accumulation points we want to be pretty small in order for this series to converge. And if the limit supremum is the opposite, it's the infimum of these accumulation points. And if it's too big, that's an indicator that the series diverges. So we'll go through that. So let's assume that R is less than 1. So the limit infimum of this ratio is less than 1. Now by BV1, so background video 1, there are only finitely many terms of this, right, that are greater than R plus some very small number epsilon. This is for any epsilon. And this is how this is defined, because it's the supremum of all the accumulation points of this ratio. And so the R is the largest accumulation point. And so there's only finitely many more than this R. Otherwise, if there are infinitely many more, then it'd be another accumulation point. And then R would be that point because it's the limit supremum. So there's only finitely many more than this. So if we let R star be R plus epsilon, then really we want R star, so R plus epsilon, to be less than 1, right? R is less than 1. So what we're going to do is we're going to pick an epsilon that's kind of halfway, the distance of halfway between R and 1. And that's what this is. See, and then that ensures that R star, which is this, plug in what we just calculated, is less than 1. Now, then, because of that R is an accumulation point, it's the limit supremum of the accumulation points, there's an n such that when n is greater than capital N, we have that every term is less than R star. So it's and R star is that R plus epsilon. It's very, very close to this R. So then now we know that if we look at our original sequence past this capital N, so it starts at capital N, and we compare it with this one. So we have cap A N, and then here we have A plus 1. But A plus 1 is, if we multiply the AN up, it is less than AN times R star, which is this term. Now if we look at this one, so now if we multiply this side by R star and this side by AN plus 1 divided by AN plus 2 divided by AN plus 1, the AN plus 1's cancel. And then AN plus 2 is less than or equal to R star squared times AN. So that's what this is. And then we can keep going. So this term is less than this sequence based upon what we've done so far. But the right hand side of this is a geometric series with R star less than 1, which converges by BV2, background video 2. Okay, so this converges. Now by background video 3, then our original the AN plus 1 plus AN, this converges, right? Because if this converges, then this converges. And we prove that in BV3. Now, this is not our original series that we set out to show as convergent, but there's only been finitely many terms removed. And if you add or subtract finitely many terms to a sequence, that doesn't change the convergence of it. Now, it may change the limiting value, but it doesn't change the convergence. So since only finitely many terms are missing from our original sequence, and it was determined to converge, then we know our original sequence converges. Okay, so that's when R is less than 1. Now we'll do it for when little r is greater than 1. And it's actually very similar. So this is the limit infimum. So it's actually the largest accumulation point of the ratios. So by BV1, only finitely many terms of this are less than R minus epsilon. This is for any epsilon. So now we want this, since R is greater than 1, we want R minus epsilon to be between these. So R minus epsilon is still greater than 1. And so we let R star be this, and then we let epsilon be the half the distance between little r and 1. So that when you plug that into this, we still have R star greater than 1. So then there exists an n such that little n greater than n, we have all the terms, once we get past this big N, are bigger than R star. And that's by definition of a limit supremum. So then if we look at this series, starting at N, then so here we have AN and AN, so those terms are the same. But if we look at A plus 1, that is bigger than yes, A plus 1 is bigger than R star AN. So if we put in AN R star, it got a little bit smaller. And then we can repeat this. So for AN plus 2, then you multiply the ratio here and multiply R star here. We can show that AN plus 2, AN plus 2 is greater than AN R star squared. And then we can keep doing this. Well, this is a geometric series. So the right hand side is a geometric series that diverges. It diverges because R star is greater than 1. And then by BV3, the left hand side diverges. Okay, so this is a geometric series that diverges, which is strictly, or it's less than or equal to this series. So this must diverge. And now that has nothing to do with our original series because we're missing finitely many terms. But adding or subtracting finitely many terms doesn't change the convergent status of a sequence. And so since this is convergent, our original series has to, since this is divergent, our original series has to diverge. And so there we've proved it. Well, that's all I have for today. Hopefully you enjoyed that. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.